Hello and welcome to Chapter 13, Part 3, Alkenes and Alkynes. We're going to be looking at the aromatic compounds for this lecture. Now the molecule benzene, which is our most commonly used aromatic hydrocarbon, was proposed 150 years ago. Now, benzene structure was quite an anomaly initially, because they found that it's only 6 carbons and 6 hydrogens in this structure, and it was extremely stable. Think about that for a second. 6 carbons and 6 hydrogens. Well, our alkenes, we said should have been CnH2n plus 2. So there should be double the amount of hydrogens plus 2 for an alkane. And we'll see for an alkene, just at least double the amount of hydrogens. It's 2n. But there's only 6 carbons and 6 hydrogens for this compound. So a guy named Kekule proposed this cyclic structure for C6H6. And it's really special because although his structure showed double bonds, the molecule did not react as if it had any unsaturation. So he proposed the structure with all of these double bonds, but it didn't actually act like it had double bonds. So this chapter we're going to kind of look at why these structures that have double bonds don't necessarily act like other structures that have double bonds. So first, why do they call them aromatic hydrocarbons? Well, they're aromatic because we think of aromatic as smelling or having a smell. In particular, a lot of these have a very pleasant smell. So like a smell from like a tropical tree. So you think of your mango trees and your palm trees. So these are going to be characterized by a much higher degree of chemical stability predicted by their chemical composition. So these are going to be extremely stable chemical compounds, with most of them having a 6-membered ring based off of benzene. So let's take a look at what this benzene structure is actually looking like. So here is the structure that Kekule actually proposed. He gave a 6-membered ring with every other carbon being double bonded. But notice that in the first structure it's single bond, double, single, double, single, double, but in the second one it's double, single, double, single, double, single, so it's the opposite. But they found that these were 2 completely equivalent structures. So after a lot of experimentation, they actually found that these 2 structures, the real actual structure of benzene, is kind of a hybrid of both of them. So the actual structure of benzene, if we were to draw it out, we said it's a hybrid of both. So if I have a single bond here and a double bond here, hybrid or average is a 1.5 bond. So in actuality, there's 1.5 bonds all the way through the structure. So it's not a single, it's not a double, it's somewhere in between. So if all of the bonds then are equal, not a single or a double, we actually are going to show that by showing a circle on the inside of our ring. So this is why that these aromatic compounds don't actually act like double bonds, is because they're actually not quite a double bond. It's about a 1.5 bond. So then what makes these so stable? Well, they actually have overlapping orbitals. So if you think back to our s, our p, our d orbitals, we said the s orbital was like a spherical shape and the p orbitals were like that dumbbell shaped or a figure 8 shaped. Well, each carbon is going to be bonded by a pair of electrons. So these are going to be those single bonds. Now, in this class, we are going to call single bonds sigma bonds. So we'll say these are single bonds, and we're going to call them sigma bonds. And the little symbol for sigma looks like that. So they're first going to have a single bond to each other. They're also going to have a single bond to the hydrogen that's attached. But the remaining electrons, those 6 remaining electrons, are going to be located in the p orbitals that are perpendicular to the plane of the carbon. So these p orbitals are going to overlap and they're going to form this cloud of electrons. Now, if single bonds were sigma orbitals, these p orbitals, these are going to be our double bonds, and we're going to call them pi orbitals. So single bonds are sigma, double bonds are going to be pi orbitals. And pi orbitals are also p orbitals. So at least that p and pi go together. Now these pi orbitals, or these p orbitals, we said that they're all going to overlap. So notice that the p orbitals are figure 8. They're all overlapping through this whole ring. Well, those 6 electrons then, if we said all of these are equal and overlapping, they can just go around in circles on the top and bottom of this ring. So it forms this cloud of electrons, so it literally looks like a circle on the top and bottom, which is why we do end up drawing the circle in the middle of these benzene rings. Now it's not incorrect to draw the double bonds throughout, but we know that that's not the actual structure. We know it's the hybrid structure, so this is the way that we show the hybrid structure. Now notice in these 3 example molecules that we have here, we're going to be looking at naming them. Well, notice the ending or the suffix of all of these. It's a benzene at the end. So we say what is attached to a nitrobenzene, or an ethyl benzene, or a bromobenzene. So for structures with benzene, we're going to use benzene as our parent name. So if it's just a 6-membered ring, we're going to call it benzene. As soon as we start attaching anything to it, so I have a methyl, so it's a methylbenzene. But notice I don't need a number out front. We know that for any 6-membered ring, or any ring, if there's only one substituent, we know it has to be labeled 1, so it's just dropped. However, as soon as I put 2 substituents on it, I do have to label where they are. So these are both equal, so I'm going to start here. 1, 2, dimethylbenzene. 1, 3, dimethylbenzene. Notice I went clockwise. If I go counterclockwise, it would be 1, 4. We said we always want 1, 2, 3, 4, 5, 1, 5. We always want the smallest number. So we always want to go in the direction that will give us the smallest number for those substituents. And then this last one, 1, 4, dimethylbenzene. Now notice down here, I've got these other names, O, M, and P xylene. Xylene is just the common name for this compound. But what are this O, M, and P? Well, in the IUPAC system, the modern day way of writing this is writing the numbers 1, 2, 1, 3, and 1, 4. However, the historical name of being able to differentiate where these are is ortho, meta, and para. I am going to want you to know both sets of naming just because you see ortho, meta, para a lot still. So although it's the older naming system, there's some people that still have not dropped it. So you see this still quite often outside in the outside world. But you also see this 1, 2, 1, 3, 1, 4. So I do want you to know both systems. So ortho is 1, 2. So whenever you have your 2 groups next to each other, it's an ortho position. If they are in the 1 and 3 position, they're always meta. And in their 1 and 4 position, it's always para. So I have a few molecules to kind of help you remember a few of these. So here are a few very common molecules. You have a paranoid, you have a paradox, and you have a metaphor. No, of course these are not real molecules, but hopefully it does help you remember that para are the opposite, so 1 and 4, and the meta position is 1 and 3. There was no fun one for ortho, but that's just our 1 and 2. So let's look at a few actual compounds that we're going to be naming. So the most simple of our aromatic compounds are we're going to call derivatives of benzene. A derivative is just a compound where benzene was our original and we added something to it. So for the monosubstituted benzenes, we're going to just add benzene to the end. So I've got a chlorine attached. Now all of our halogens, we drop the ending and add an O. So this is a chlorobenzene. Our NO2 is a nitrobenzene. And then our just normal alkane group, 2 carbons, ethylbenzene. Now if we do have substituents that are different, well, then we're going to name them in alphabetical order, just like we have in the past for our alkanes and our alkenes. So the first named group is always in position 1. Now, if they are different groups, we're going to say that the special group must be the position 1 on a ring. So you go, what is special? Well, it's typically another functional group or something other than carbon. So if there's a group with a nitrogen or an oxygen or a sulfur or something other than our carbon chains, that is typically going to be our special group, and that's going to have the designation number 1 on our rings. So then we're going to either, if there's 2 of them, name it 1, 2, 1, 3, or 1, 4 on our rings with ortho, meta, and para. Now, like I said, you're going to see it both ways. So you're going to see both ortho and a 1, 2. You'll see it on both your homework and on your exam. So like I said, I just want you to think of these as interchangeable ways of writing them. So here are a couple examples of our substituted benzenes. So for this first one, I have an ethyl group and a bromine. We said that the special group is something other than carbon. So I've got a bromine, so that's going to be 1, and then our ethyl group would be 2. These are also in the ortho position, so it's an ortho bromoethyl benzene. So basically I'm just dropping the numbers and putting an O out front for our ortho position. For chlorine, I have chlorines on 1 and 4 position, so it becomes a dichlorobenzene. Or a para or p-dichlorobenzene. Now I put this last one on here, and you notice this one's a little bit different. This says toluene at the end. You go, toluene's not benzene, so what the heck? Well, toluene, we're going to find is actually this structure right here. It's the benzene group with a methyl. So toluene is essentially methylbenzene. Now this is so common that instead of writing methylbenzene, historically, they just called it something toluene. However, we want to name this as a benzene group, so you won't need to know that it's toluene. What you will need to know that it is 1 nitro 3 methyl benzene, or that it is a meta nitromethyl benzene. So these benzene names are the ones that we are going to be focusing on for this chapter. Like I said, these other historical names, you will see them quite often, which is why I do put them in here. You will see the term toluene fairly often in this class and in other classes, since it is such a common molecule, and it's its historical name. So here are just a few of the other historical names that you'll see often. Like I said, you will not need to know these names, but I do want you to be aware of them, so if you see them somewhere else, that it doesn't get confusing to you. So we said that methylbenzene is called toluene. Our alcohol group on a benzene, we would call a phenol. We're going to see when we start naming alcohols that an OL gives us an al. Sorry, an alcohol gives us an OL. And then our aniline, we've got a amine group up here. And then benzoic acid, we've got our carboxylic acid group up here. So you will see these frequently, just don't get confused that it is a slightly different naming system. I will not test you on these names in particular, however. Alright, so what happens if I have multiple functional groups in a chain on a carbon or in a carbon chain? Well, if I have a long carbon chain, so here's my long carbon chain, and I've got a functional group in that carbon chain. I can't name this benzene something rather because I've got this double bond. There is no name for this group here. So if I've got a long carbon chain with another functional group, benzene actually becomes a substituent of that carbon chain. So we said that if we see a double bond, that double bond is where we are going to start numbering. So in this case, we would start numbering 1, 2, 3, 4, 5. So we have to start numbering at that double bond. So then when I have a benzene ring as a substituent off of that carbon chain, it becomes what's called a phenol group. Sorry, a phenol group. So phenol is our benzene ring. The reason why I want to specify is because phenol, we just said, was a functional group. So it was an alcohol off of our benzene ring. So phenol is our substituent. Phenol is our functional group. Now we said that these groups are super stable. So these benzene rings and anything with this aromatic compound are super stable. Just because they're stable, however, doesn't mean that they're necessarily good for us. So let's take a look at a few examples. So I have naphthalene here. So I've got two benzene rings together. So we're going to call these polyaromatic hydrocarbons, or PHS. So two aromatic compounds, naphthalene. This is actually the main ingredient in mothballs. So mothballs are something that you put with clothes that you're going to be storing for a long time to keep bugs from eating them. So they emit an odor to keep bugs away. We said they're aromatic, so it kind of makes sense that they emit an odor. However, it doesn't smell very good. So it's not something that you want to be exposed to all of the time. And that's why you always have to air out clothes that have been stored for a while if somebody put mothballs with them. We'll find that all of these are kind of produced using kind of dirty methods. So this anthracene is produced from coal tar. And it actually is the reactant to make red dye. So a lot of the red dye that we use in clothing comes from this anthracene. So although these first two have good uses, these last two do not. So this phenylanthranine and this benzopyrene, these two are also found in coal tar, but they're also found in cigarette smoke. So these two compounds are part of the reason why secondhand smoke is so toxic and irritating and can cause cancer, because both of these compounds are cancer-causing agents. So this first one, this phenylanthranine, that's pretty much all you've seen it as is in cigarette smoke. But however, this benzopyrene, you actually see this being produced anytime that you cook something at a very high temperature. So you think of cigarettes, you have to light it on fire and then you produce all of these extra toxins. Well, this also occurs with this benzopyrene for when you cook food. So you cook meat at a very high temperature and you kind of get that charcoal on the meat. Well, part of that stuff in the charcoal is this benzopyrene. So this is why you say, you eat a lot of red meat, it could be bad for you. At least part of the reason is that you typically cook them at higher temperatures and you produce these extra cancer-causing compounds when you cook things and you get that charcoal on that food. Now, it's not just the multiple rings that can be cancer-causing. Just the single ring benzene is also known to cause cancer. So benzene is actually a very pleasant smelling, pretty compound. Just the straight benzene has a rainbow shimmer to it, and it actually smells really nice. We use benzene a lot to make polystyrene, so to make styrofoam. So it's also a very useful compound, but That's also why styrofoam doesn't degrade. That's why when you throw styrofoam away, it doesn't go away in the landfill. It doesn't start to degrade at all. We know benzene is super stable, which is why polystyrene or styrofoam is super stable. Stable means it doesn't want to react. It doesn't react, it doesn't go away, or it doesn't react into something else. Now, as for the cancer causing, benzene in particular causes a lot of leukemia. You go, that's not a problem. I've never been exposed to benzene. Well, back in the 1950s, benzene was also found in most garages. Benzene is a very good solvent for other organic compounds. So our grandparents or great-grandparents actually used it to clean up oil spills in the garage. So anytime they spilled a little oil, they'd put a little benzene on it, wipe it away, and throw that away. Well, when they found out that benzene was super carcinogenic, they banned all benzene for personal use. So you can't go down to the store and buy benzene anymore. But our grandparents could. It was a very common substance for our grandparents. So kind of interesting how things evolve, and we find that, oh wow, that really cool thing that we've been using for a long time actually causes cancer. So I'm sure that we are using something in our household right now that is a very similar product. We'll see that Teflon, we'll look at Teflon here in a little bit, and Teflon was one of those things. It's also super useful, it got everything non-stick, but they found that Teflon causes cancer too. But so they've reformulated it, and most of our pans no longer have Teflon in them. But we probably all were exposed to some Teflon at some point, which if you see any Teflon anywhere, do not use it, because that is another one of those cancer-causing compounds that we initially thought were good, but now know that they all have some adverse effects. Alright, so let's look at a few more of the reactions that benzene actually does go through. So we said that benzene does not readily undergo addition reactions. Benzene is super stable, it wants to keep that ring solid. If I start to go and add other bonds to the molecule, well then I'm going to disturb that ring on the inside, that cloud of electrons, and it's no longer very stable. So it doesn't want to add anything to it. However, what it will do is it will substitute those hydrogens. So you can take a hydrogen off and then add something else to it. However, we've said that this is super stable, so it needs a catalyst every single time. Nothing will react with benzene without a catalyst. But we can do halogenation reactions, nitration reactions, and sulfonation reactions with our benzene. So let's first look at this halogenation reaction. Now, just like our alkenes, it's mostly going to be with bromine and chlorine. So these are the most reactive of our halogens for our alkenes. Typically have a catalyst of iron or iron chloride. So let's take a look at how this chlorine is going to react. So whenever we have our reactants, always expand them out because it's going to be easier to see how it's going to react. So instead of saying Cl2, let's write it Cl and Cl. That way we can see that this hydrogen is going to transfer its electrons to this chlorine, and it's going to pop off and form HCl. The chlorine then that got left alone then is going to transfer its electrons back to the ring, and I will get the chlorine now attached to our benzene, so I've got a chlorobenzene. So the hydrogen attacks one of the chlorines, or the chlorine attacks the hydrogen, pulls it away, and then the other chlorine goes in and attaches to our ring. So we see this happen a lot with our dinuclear compounds, so our compounds that have two atoms. One of them is going to take something away, and the other one is going to be added. So let's look at our next reaction. Benzene nitration. So nitration places the nitro group on the ring, and we need sulfuric acid as a catalyst. When we add nitric acid and sulfuric acid together, it's actually called fuming sulfuric acid. It's an extremely strong acid. So this is not something light that you do to this ring. We are really making it caustic to be able to make this reaction occur. So if we remember, there are hydrogens all around this ring, and we have this nitric acid now. Now this NO3 has two double bonds and one single bond for the oxygens. Now one of those oxygens doesn't want to attach to the ring. It makes it very unstable. It has too many electrons. So what's going to happen is this hydrogen that's attached to the ring, this hydrogen that's attached to the nitric acid, and one of the oxygens are going to get pulled off. So I'll have this H, and one of these O's. So the NO2 gets attached to the ring, and one oxygen is left over. And we know an H and an O and an H make water. So although we start with nitric acid, we're actually creating water as a byproduct, and the nitro group NO2 gets attached to the ring. Now remember how I said that all of these double bonds of this nitrogen group have a lot of electrons. Well, if they have a lot of electrons, it's very electronegative, and it actually pulls even more electrons from the ring towards the nitro group. So it's actually destabilizing the ring by adding this NO2, since it's actually pulling some of that electron density away from it. So this makes it a very unstable compound. Now let's look at another compound name real quick. I'm sure you've heard of this one for sure. So it is trinitrotoluene. You go, Professor, I've never heard of trinitrotoluene. Yes, you have. Where have you heard it? It is TNT. So trinitrotoluene, I add 3 nitro groups to this toluene ring, and it makes an extreme explosive that we are all familiar with. So let's take a look at what this compound looks like. So we know we got to start with a benzene ring. It's a toluene, so I'm going to add a methyl group on, and then trinitro. So I have 3 nitro groups. So NO2, NO2, and NO2. So notice how many NO2s are there. We said that these groups pull electrons away from the ring. Pulling electrons away is destabilizing the ring, and that's what makes it explosive. So it's because we have all of these nitro groups on there that makes TNT so explosive. So I just showed you how we can add nitro groups to our ring, but I'll leave it at that. So that way we don't necessarily learn how to make our TNT, but I'll tell you that if the Unabomber can make it in his shed in the backwoods of Oklahoma, it is not a complicated reaction to add all of these nitro groups to the benzene ring. Alright, so let's look at our last reaction, our sulfonation. So the sulfonation places a SO3H group on the ring, and we also need that concentrated sulfuric acid as our catalyst again. So this is going to be our substitution reaction. So I'm going to basically substitute this SO3 into our group. So basically we're putting this SO3 into our ring. When we do that, I now have the SO3 placed into the middle with the hydrogen, and I'll produce some water as our byproduct. Now, this is another compound that you look at and go, I've never heard of benzene sulfonic acid. Well, actually you have. Benzene sulfonic acid is the most common ingredient or active ingredient in laundry detergent. So if you look at a lot of your laundry detergent, you'll see that benzene sulfonic acid is one of the active ingredients to create or to clean our clothes. So it's interesting because a lot of these compounds that you go, oh, I've never heard of that, but in actuality you have. Organic chemistry is really all around us every single day. So those are the three reactions that I want you to know for our benzenes. But let's look at a few other aromatic hydrocarbons. Now up till now we've had only carbon in our benzene rings. Now we've got a nitrogen and oxygens and sulfurs in the ring as well. These also have the pi orbitals or the p orbitals that can overlap. So we can still create stable rings with these heteroatoms in there. Now most of them will be the 6-membered rings, but we do have a few 5-membered rings as well. Which is interesting because you can't have every other carbon or every other double bond with these 5-membered rings. But we know that it's not actually a double bond. We know they're all like 1.5 bonds, and it's just that the pi orbitals or the p orbitals have to all overlap. Now one of these compounds in particular is a very good base or good base reactant for a lot of organic chemistry. So this pyridine, they use it a lot as a reactant to create other compounds. The catch is that pyridine is one of the worst smelling compounds I have smelled in my entire life. This is your rotten fish that have been sitting out in the sun for days smell. So it is still aromatic, it still smells, but they don't necessarily all smell good. This is one that absolutely smells terrible. Even when it's in a hood in a chemistry lab, you will still smell it as soon as somebody opens that bottle. It is that potent of a smell. Now these other ones don't smell that bad. In particular, it's just this one nitrogen in a ring that creates that terrible smell. Now we're going to be looking at these heteroatoms in rings more when we look at DNA and RNA, because these are actually the bases for some of our amino acids. So having these nitrogens in the ring, we're going to see it a lot in our DNA and RNA molecules. So I just wanted to kind of make you aware of it right now, and then we'll focus more on it when we get to those chapters. Also, we also have a aromatic ring found in our hemoglobin or chlorophyll in plants. So these stable compounds are very biologically active, and so I say active, it's because these nitrogens make it active in these sites. So the extra lone pair on these nitrogens make it reactive in our bodies. Okay, so just a quick review of all of our alkene structures or our alkene reactions. We can do a hydrogenation. Now this is our hydrogenation for our fatty foods. So you'll see that it's a hydrogenated food. All that means is you're adding hydrogen to those double bonds. We also have our hydration, which is adding water with an acid catalyst. We can have our halogenation, adding a halogen. Remember, X is just some halogen. These add so easily they don't even need a catalyst to our double bonds. And then we have our hydrohalogenation, or it's like HCl, HBr, and those add across a double ring too. So those are our alkenes. So those were those 4 alkene reactions. We also know that we can create polymers with our alkenes, so our polyvinyls. And then we have our 3 reactions for our benzene. So our halogenation, nitration, and sulfonation reactions. So that's a summary of all of the reactions I do want you to know for this chapter. And here are the examples of all of them, so you have a quick reference. So if you want to do a hydrogenation, well, we know that we're going to add a hydrogen across a double bond. So you find the double bond, add the hydrogen, and we get an alkene. Hydration, we're adding a hydrogen and a water or an alcohol, and we create an alcohol group. Adding our halogen to each side of that carbon, creating an alkyl halide. And then our hydrohalogenation, adding the H and X. Remember, we used the Makhonikov's rule for this, and whichever carbon has more hydrogens, that's the one that the hydrogen is going to be attached to. We have our polymers, where we basically cut off those hydrogens or cut off the double bond and create links through the whole chain. We have our 3 benzene reactions, and we did today too, adding the halogen, our SO3, and our HNO3 as well. Alright, that is the end of chapter 13. I will see you again in chapter 14.